It's going to be quantum computation. So the main aim will be, rather as in the case for classical, we want to know exactly the gates required to be able to implement a quantum circuit. So let's just recap what we know about classical. So we proved that in the introduction, something like fan out and NAND, and also just by and or not, for example, are universal sets in the sense that any classical circuit can be implemented with just the gates in one of these sets. And so in the case of classical, that's what we're trying to do, is we're trying to implement all functions from 0, 1 to the n to 0, 1 to the n. And in the case of classical, what we want to implement is all unitary transformations, okay, on n qubits. So we want to, in a quantum circuit, we say a set of gates is universal if any unitary operation can be implemented using only gates from this set. Well, that's really not quite true, because unitary transformations are in a continuous over the complexes. So we've got a continuous set of things. So we're never going to be able to give you a discrete set of gates for a continuous. So it's only up to arbitrary accuracy. So up to, well, how do we say that? Arbitrary accuracy. I'm not sure I know how to spell accuracy. Yeah, so that is going to be our main aim in this chapter. What we're going to also do is, along the way, analyze some quantum circuits, which will help us later as well when we do quantum algorithms and quantum error correction as well. Yeah, so some comments here. Firstly, remember that we already showed that a Toffoli gate we can implement any classical gate, any of these classical gates with a Toffoli gate. So we already we proved we can implement classical gates with the Toffoli. So these are our quantum circuits will subsume all the classical circuits. So put briefly, so quantum subsumes classical, but of course we want to do a lot more. Okay. So that's going to be our plan. So we want to find a set of gates which is universal for quantum circuits. And when we mean by universal, we can implement any unitary operation up to an arbitrary accuracy. Now, why is that important? It's kind of important for classical, but not really. I mean, you're never going to write, actually, if you think about our solutions for fan out and NAND being universal, you're never going to implement that on your circuit board. You're going to do it, you want to use upper least space as possible and whatever and nor not circuit gates you want to put, you want to kind of minimize the number of gates and make your circuit as small as possible. Now, for quantum computation, it's extremely important to know what is a universal set of gates, because when we come to the algorithms, we'll have an algorithm and we want to be able to implement that in our quantum circuit. And it's very, very difficult when you're trying to make a quantum computer to actually implement these gates. So it's incredibly important to know that what will transpire is that you only need to be able to do 3 different things. And if you do those 3 things, then in theory, if you could scale up, you could do everything. Okay, and that's incredibly important. So for people working in a lab trying to make a quantum computer, these 3 gates are absolutely fundamental. Yeah, that is what they're trying to do. So when you see a reader report, a newspaper or something, or in a science magazine, they might say, yeah, and we've managed to implement Hadamard gate, why C0 gate. Your eyes will suddenly light up. Okay, so that's the plan for Easter, to understand that is the crux of the problem. Okay, on a practical level. We'll have to at some point confront the actual problem. Engineering problem, let's say, of actually constructing all of these things. But for the moment, let's focus on the job in hand, which will be to prove then. So go over, say it again. So any quantum operation, any unitary operation, so it can be implemented up to arbitrary accuracy by just a small set of gates.
What does up to arbitrary accuracy mean for, like, in this context?
Yeah, we will get to that. So we will define what we mean by close enough. Okay? It will turn out to be some kind of exponentially negative exponential, so we will be very happy. I mean, the thing is, Adrian, since everything is always a bit probabilistic, there's always that probabilistic factor in a quantum circuit. There's always going to be some, if you like, error. So you're always trying to minimize the errors, and then maybe you have to repeat your algorithms to. But if the error,
that's one thing. But like, we could, like, you can make the randomness like perfectly, like the same way you could perfectly replicate a quantum state. Like you didn't get a quantum state that was close enough to the original. You got an exact copy that behaves as randomly as the original did, but it was still like equal, right? Like it was that sort of thing what I was asking. Like there you have no error. Like you perfectly replicate the original with, and like it's random in the same way that the original was. So like there you sort of have no mistakes.
Yeah.
Here it's going to turn out that you have to. Right?
Yeah,
So it's not the same. Like,
yeah. Okay, so let's say I want to show you where we're going to go. Yeah? So this is so we want to show we will prove the following, just so that you know, because otherwise we might get a little bit lost on the way. Okay, we will show you first that any unit, well, not necessarily in this order actually, any unitary map, any unitary operation can be decomposed into two-level unitary operations. I only affect, only act. By two-level unitary operations, I mean they only act non-trivially on two coordinates, or at most two coordinates.
Right. So the two level doesn't mean that it's two, like there's two of them, or like two level is like sort of the combined like two level unitary operation or two level unitary operations. Like this is the, okay, yeah, that.
Okay, so for example, a matrix might be oops, that should be a function. Well, I just got ABC here because it's unitary, it's not Hermitian, necessarily Hermitian. So this, for example. Okay? So this would be only acting non-trivial on two coordinates. The first, the second, and the fourth are unaffected, and it just does something with the third and the fifth. And when I mean decomposed I mean U is going to be U1 times U2, U something. Okay, and all of these are going to be two-level, like this. Okay, so that's something we have to prove. We'll get that. That will take up most of today. Now, any two-level unitary matrix, so any two-level unitary operation can be implemented with Toffoli and a controlled U, which I'll tell you what they are in a minute. A controlled U. Okay, so that will be our 4.1, which we're going to get to in a minute. 3, any controlled U can be implemented by a C naught and a single by a C naught, so control naught, which we already did see, and a single qubit operations. Should be operator, really. It is going to be one of the exercises to prove for any TOEFL can be implemented, well, TOEFL can be implemented by a CNOT and single qubit. Okay, so we have just going down from 1 to 4. This is already, I'm going to leave as an exercise. This is exercise 4.4. So the exercise, I think I've forgotten how to write exercise. 4.4. So that one I'm going to skip, or we'll do together. So if we follow this 1, 2, 3, 4, we see that we're already down to CNOT and single unitary operations, and the epilogue, which we'll get to at the end then, is that at the moment there's no approximation, so 5 will be any single unitary operator can be approximated by Hadamard, which was this, and T8, which is this. Okay, so it's going to take us a little while, but then you see how absolutely important this is, because when somebody is in the lab, what they're really trying to do is just implement these 3 gates, because in theory, then that will be it. Okay, if only you could scale up without getting problems with the noise, which we'll come to later as well. Okay, so that's the plan. So first things first, I have to tell you what controlled U is. I don't know if we saw that in the introduction. So 4.1. Control U gates. Yeah, so it's the classic if A, then do B. Classic thing. So here we already saw that an example was the C0, which was denoted like this. So recall that this upper wire corresponds to the first qubit, the lower wire to the second qubit. So this would be take 0, 0 to 0, 0, 0, 1 to 0, 1. So if this is not set, don't do anything. If it is set, then we flip. We do addition modulo 2, which results in this getting split. So this is actually just equal to, this is the same thing as saying, this is a controlled X. Okay, so now we see what a controlled U will be. A controlled U will be apply U if the first qubit is set to 1. Now recall, why is this absolutely fundamental? Of all the things, this is really the fundamental gate, because it is the C naught which allows you to do entanglement. So recall, if here we place a Hadamard before our C naught gate, and we start off just in 0, 0, then at the end of this is where we ended up with our Bell state. So let's just go over that again. So we apply Hadamard to the first, okay, so that will take us to a plus. That is actually equal to 0, 0 plus 1, 0. And now we apply the C naught gate, and this goes to 0, 0, 1, 1. And this is an entangled state, yeah? So this is entangled. And it's entangled on more than superposition, which allows us to really use the power of quantum mechanics to do our computations. Okay, so the C naught gate, absolutely fundamental. So we're going to be showing that this control U can be implemented. So we'll prove this can be implemented by a single qubit and C naught. Right, so let's just first have a little delve into calculating some quantum circuits, because we will do that in the exercises. So I thought it was unfair if I put them in the exercise and didn't do any of them myself. So I will just do a computer couple of examples myself, and then you'll see how this works. So, for example, what would this circuit do? So, I mean, you can pass away hours. To do on top of there. On long journeys, writing down small quantum circuits and thinking, oh, what does that one do? Okay, so as I say, it's the same as this. So we just, the way I do it, there's two ways of doing this. Or you can try and write down the matrix, or you can just see what happens to the elements in the computational basis. Personally, I prefer to do it like this. So 0, 0. It's going to be Hadamard. Nothing goes here, and then Hadamard again. Okay, so we see straight away that that just goes to, well, okay, let's do it. It goes to plus 0, sorry, 0 plus 0 plus. Does not apply to Z because the 0 does not apply the z here because it's 0 set in the first qubit. So that just goes back to 0, 0. If you get 0, 1, then there's, well, again, nothing happens. This goes to minus. So recall that the, so here I'm using the fact that plus is this gate and minus was this gate. This qubit. So this then doesn't get applied because I've got a 0 here, and then so that's the same, and then I apply another Hadamard, which takes the minus back to a 0, a 1, sorry. And now 1, 0 goes to 1 plus, which I will write out. This is 1, 0. That's 1, 1. And now I press, now this Z does come into play because I have a 1 in the first. And what it does, the Z, well, if you recall, Z is matrix 1, 0, 0, minus 1. So here it's not going to do anything because I've got a 0. This is a square root 2. So here it's going to be 1, 0. But here, the 1 is set, so I've got to apply the Z. I've got a 1 in the second qubit, so then the sign changes to a 1, 1. And now I have to apply Hadamard again to the first qubit, so that's going to be 1, second qubit, sorry. So that's going to be 1 plus minus a 1 minus. And now I have to stick in the pluses and the minuses. The 1, 0 is going to go with the 1, 0. It's going to disappear. And I am going to get 1 over 2 times 2. Sorry. Here I'm going to get a 1, 1. And here I'm going to get a 1, 1 as well. So the answer, after all that, is 1, 1. And then the final one is 0, 1, which is going, sorry, 1, 1. Which is going to go with the Hadamard to a 1 plus. We're then going to apply the Z. Which in the first one term does nothing because we've got a 0 here, and the second one switches it. Now I'm going to play this Hadamard, which is going to give me 1/2. Well, 1 over root 2 if I put the pluses in. 1 plus minus 1 minus. And as in over there, that. Ooh.
Yeah. Does the 1, 1 map to 1 minus or 1 plus?
Yeah. Thank you. I was doing the same. I was doing the same one as before. And so when I sum these two, these bits cancel, and then I get left with the 1, 0 here. So this is then equal to 1/2 twice 1, 0. Okay, so after all of that, what I've managed to ascertain is that this circuit, sorry, is exactly the C0. Okay, so this is equal to this. Yeah, all this, these two didn't change. Here what I did was change the 0 to 1 the second bit and the 1 to the 0 the third. So there's a whole load of whole list in Nielsen and Chuang, some of which I copied out into exercise 1. I should do one more, which isn't quite as complicated as that. And then we'll get on with the job in hand. So here's another, so this is slightly easier. So they're quite, when you look at them, you think, oh, doesn't look like it will be equal, but then it is. So I expect you all to become experts at doing these things. Okay, so let's work out what this one is. So 0, 0 goes to, well, nothing happens here, nothing happens here, nothing happens anywhere. So that goes to 0, 0. 0, 1, nothing happens here. That is just automatically applied. That's not a control. So that will go, that will then pick up a minus, and then nothing will happen here. The 1, 0, that will be then going to 1, 1. That will then go to minus 1, 1. And then that will go to minus 1, 0. Whereas here we go 0, 1. Sorry, 1, 1. That will split the second bit. This will then do nothing. And this will then flip the bit back again. So go 1, 1. So can we simplify this? Well, yes, because these two are basically applying Z operations to the two bits. And this first one, if I do it like this, then this is coherent, nothing happens. This will give us a minus sign because of this Z here. This will give us a minus sign because of this Z here. And here, they will both try and flip the sign and end up flipping it back to nothing. Okay, so this, in fact, is equal to that. Well, it's easier when they tell you what it's meant to be equal to, I have to say. Otherwise sometimes it's a bit more difficult. Right, so anyway, so there's quite a few of those on the exercise sheet to have a go at. Now, more recalling. So, at some point in the introduction, we defined these so there should be an identity operation there. R operations, and similarly for X and Y, but X and Z. And we proved that if you look at the representation on the block sphere, then this was a rotation about the y-axis through an angle of degree theta. Now, at some point in this proof, no, maybe not this proof. Maybe that's the next one. Okay, so we will be trying to prove in this first lemma. So we're going to have one lemma, and then after we've got this lemma, we will be able to prove that you can implement a controlled U as a single qubit operation and a controlled NOT. And it follows from this lemma, although, to be honest, you probably won't see it straight away. Okay, so suppose U is a single qubit unitary operator. Then there exist alpha, beta, gamma, delta. So that's that. This U decomposes in the following way. E to the I alpha. Let me get that a bit clearer. So that's going to be our first proof of the day. So our U in matrix form is something like A, B, C, D. It's unitary. So when I look at the Hermitian conjugate and I multiply them together, this has got to be the identity.
Wait, is the first Z supposed to be an X or it's correct that it's a Z?
No, it's a Z.
It's a Z? There's no X? Oh.
Yeah, no, there's no X. Oh. No, because it's, I mean, if you think about the Z, it's, yeah. Well, you'll see why it's a Z. So this product here must be the identity matrix. Now we can already, what I want to do is kind of like do a change of variables here. And somehow we've got to get to the fact that it's meant to look like these kind of rotation matrices. So the first thing to notice is this AA plus BB equal to 1. Well, that implies that the modular for A is at most 1, okay, because this is a positive real number. So it's this, and it goes sum to 1. So we can write A is equal to e to the I capital A cosine of some angle. Okay, I know that's a bit weird, but that's what we're going to do, right? Okay, so this is some number between 0 and 1, and then I just got to, or if you think about the complex plane, I've got to find something like just move it around a unit circle by an angle A, capital A, until I get to wherever my A is. Okay, so that's fine. And now when I look down here, this is going to imply that A is cosine of theta squared. So here, this B is going to, this implies that B is of the form e to the I B sine theta. Okay, cosine plus sine squared is 1. And similarly, I'm going to, for the C and D down here being equal to 1, similarly, C is going to be e to the IC cosine some angle, which implies that D must be e to the ID sine that angle. Okay, so that deals with the 1 and the 1. Now I have to get these zeros. So A C bar plus B D bar equal to 0. That is going to be, well, let's just be brave and do it. E to the I A minus C cosine theta. And now I'm worried that I probably put these sines and cosines around the wrong way. Yes. So I wanted to, I mean, I can choose arbitrarily that to be the sine and that to be the cosine. So if I choose that to be the sine, then this must be cosine. Right. Sine plus BD needs to be I, B minus D, sine. So that's that one. And then the other one, which was the conjugate of this. Right, so I've got two equations, and here I have a minus. Why have I got a minus here? Because I can arbitrarily choose this. Okay, I mean, this angle going round, that's just making this angle more divided by 2, and it doesn't change the fact that this is going to be 1, because I have a minus here. And now it does change something oh, sorry, that's the B that changes. So B, I put a minus here. And now that does change here. It gives me a minus. And here as well. Right, and the reason I want to do that is now because I can now make these two conditions satisfied. So these are then satisfied. Taking A is equal to A minus C is equal to B minus D, and theta is equal to I. Okay, so then we will get an identity. So now I need to do a change of variables to see where the alpha, beta, gamma, delta come from. Let's just leave that up there for the moment so we see where we're going. So now change variables. So now set A is going to be equal to, let me get this right, alpha minus 1/2 beta minus 1/2 delta. B C, it's going to be plus minus. And now D is fixed because it must be satisfying this, and it must be fixed with plus plus. Okay, so yeah.
Aren't the two equations one the conjugate of the other?
One is conjugate of the other, yeah.
So, I mean, then you only needed one of them. If a complex number is 0, its conjugate is also 0.
Yeah, but it's a complex number, so it's got two real parts, right? So I think I've got to get them both being 0. So if I wrote this out, as a complex number, cosine of this plus I of this, I sine of this, and likewise here, I'll get a real part and an imaginary part. And both of those two have got to be 0. And no? So that gives me 2 conditions. And so I get, if this is certainly a solution, right? Who asked the question?
Yeah, it's a solution, but I don't see why it's the only possibility.
It may not be the only possibility. Oh, because you see,
But it's almost the only possibility, right?
no, it should be the only possibility. Yeah.
In the first, you take one of the terms into the other side, and you look at the direction of the in the polar form and the modulus of the number. You will end up there.
Yeah. Agreed. Who said that?
Me.
Edgar. Very good.
Okay.
I
like it.
I agree. You don't need both equations. You don't need. You're right. I mean, you just look at this equation, and this is the equation of complex numbers, which implies this. Right. I mean, the angle going round has got to be the same, up to 2 pi modulo 2 pi. Yes, Edgar? Is that what you wanted to say?
Yeah. That was the idea.
Yeah. Okay. So, and here, this is now satisfied. This d is now fixed, right? So this here I have 4 variables with 1 equation. So the solution has 3 degrees of freedom. And you can check that A minus C is equal to B minus D. So all told then, we have now that, so this is where we're going. Should I leave it up there? So now we have that U is looking like this. So this is what we're trying to do. So U is equal to I think we can already take out the e to the I alpha. I think that's obvious. Here we have e to the minus half beta minus half delta I cosine thing. The b AB minus half. There's a minus here. Sine. Here's the C, which is I, and the D. Oh yeah, these are equal. Okay, so yeah, so we need to now prove that this is the same as we had before. We have to prove this is the same as this. So let's just do that up here. So RZ delta, that's cosine delta divided by 2 times the identity minus I sine delta over 2 times Z, which is a matrix, is cosine delta 2 minus I sine delta 2, 0, 0, cosine delta 1, 2 plus I sine delta 2. So this is, in fact, e to the minus I e to the I. Okay, so that's that matrix. Similarly, with the RZ beta, so the RZ beta is basically the same, right? So that's just changing. Delta to the beta. I think you're almost on your ways to seeing it now, right? Because once we write down Ry, now how is Ry of gamma? That's going to be cosine gamma over 2 identity minus I sine gamma over 2 y. Recalling that y is 0 minus I 0, this is going to be cosine minus I squared is minus sine, so that must be plus, and here. Okay, so this is going to be that. And when we multiply these things together then, so Ry gamma Rz delta, that's going to be this times that one. So you're going to get e to the minus I delta 1, 2 cosine. E to the I delta 1, 2. And it should be matching up, right? So now when we multiply by the RZ delta, RZ of beta, sorry, of this thing, and this is going to, well, you can see it now, right? Because now I have to, if I take RZ beta, I have to multiply the first row by e to the minus I beta 1, 2 cosine. Sine. And the second row by positive beta. And that's the same. Okay, so now all you have to do is multiply by the e to the I and check that these two are in the same. Okay, so we have to set gap theta equal to gamma divided by 2. So, conclusion. And it's so innocent, it looks so, I don't know, it doesn't look like it's going anywhere. I mean, you do all this work and you finally work out that u is equal to some real numbers. So I should have said they're real numbers. So, that's it. And this is amazingly enough to prove the following theorem. Control U can be implemented by C naught and C. I don't think we actually need that anymore. No, okay. We don't need this. And here's the proof. So we're going to define our 3 single qubit operations in the following way. This is going to be Rz beta Ry of gamma divided by 2. B is going to be Ry of minus gamma divided by 2. Rz of minus, what am I missing? Beta plus gamma, beta plus delta divided by 2. That's going to be our second one. And then the third one is going to be C, which is going to be R of Z of the things we make that 0. So that's going to be minus beta divided by 2. That's minus beta. Okay, and the first thing to recall, so recall that R is rotation through angle theta along the n-axis of the block sphere. Okay, so now you see why we were so bothered about proving these things in the introduction. So this this operation here is rotation along the z-axis by this amount of degrees. Okay, so let's work out what happens if we do A times B times C. Okay, so C is going first, it's going to rotate it along the z-axis by delta minus beta divided by 2, and then the B does the same thing, but rotates it from minus beta plus delta. So here we've rotated, so this is going to be here a rotated by Z through the minus beta. Here, when I multiply the A and B, I'm rotating around the y-axis by minus gamma divided by 2 and plus gamma divided by 2. So that cancel each other out, and here I get rotation around the z-axis by an angle beta. So when I multiply all these things together, I get the identity. Just using the fact that this we proved in the exercises in the introduction that this R can be interpreted as rotation on the block sphere. Now, what happens if I do x, y, x? Well, x and y anti-commute, and x squared is 1. So here I'm going to get minus xy, which is minus y. That means that if I do x, ry something, I don't know what it's going to be, let's put theta, x, then I get Well, let's write it out. This is cosine theta times the identity minus I sine theta times y x. And you can see what happens here is that I get xx, which is just the identity, and the xyx, which is minus y. So the sign here changes to a plus. So that's just the same as doing rotation of a degree minus theta. So then, and now for the big thing, what happens if we stick x's in here? So let's do that. Let's leave that up. I'm going to go off the theorem because we know what we're trying to prove. And let's see what, let's calculate. So A, X, B, X, C. You can't see it, but Adrian's face just dropped. But it's not so bad. It's actually not that much to do at all. Because, well, okay, let's just write it down. So we've got RZ beta, RY gamma divided by 2, X, RY minus gamma divided by 2, RZ minus beta plus gamma divided by 2, X, or maybe he's right, RZ. Okay, that's it. So what we've just decided that if we see an X, R, Y, X, we should just change the sign of the angle. So let's stick a couple of X's in to make that happen. Let's put an X both here and here. Now X squared is identity, so that's fine. And now what happens when we apply our identity here below? This flips the sign there. Here it flips the sign as well. So I get R of Z. Is that gamma's a delta, right? That gamma's a delta. Otherwise, it doesn't make any sense. Okay. And now we see, since rotation through an angle of gamma followed by gamma divided by 2 is just rotation through gamma, and here I'm rotating along the z-axis twice, so I can just sum the angles, and I get delta. Ooh! But now, if I look up here, this is almost u. This is almost u. This is e to the minus I alpha times u. So I can kind of see, so I only now have to be a little bit clever and design my circuit using the fact that ABC is equal to the identity and AXBXC is equal to u. Do you see where the C naught's coming from now? Yeah, it should, I reckon you should be able to finish it off, but anyway, hold on. So, bearing in mind this and ABC. One, so I'm just copying that back up. I'm now going to draw for you the circuit which is going to implement the C naught gate the control U gate using just C naughts and single arbitrary qubit operations. And here it is. So I want the C to come first. Hits the C. I want to apply an X, a C naught gate, then a B, and a C naught gate, and then the A. And here, well, I've got a slight problem with this e to the I alpha here. So here I'm going to apply the gate 1, 0, 0, e to the alpha, and we'll see why in a minute. Okay, so that kind of fixes things up. Okay, so now I claim that this is a controlled U. So this only uses single qubit unitary operators, 4 of them, and 2 C naught gates. Why is this the same? Well, what happens, so I just got to check the basis, right? So what happens to 0t? Well, it's going to get multiplied down below by C, then B, then A. So it goes C, then B, then A. That's the identity. So nothing's going to happen to it. And at the top, this 0 is just the 1 here, so that just goes to 0t. And now what happens to 1t? That's going to be going to 1, and then it gets a C, then an X, then a B. Oh, I'll run through. You get C, then an X, then a B, then an X, then an A. And meanwhile, this 1 here is getting multiplied by e to the I alpha. So this is then e to the I alpha 1, e to the minus I alpha u to t. And of course, if you think about this, this is actually...
It's just u, right? Like the e to the minus I alpha u, it's like it's not e to the alpha times u, it's just u, right?
How do you see that, Adrian? I mean, it's because of this. This is just a tensor. So I can just take this over here. Is that what you're saying?
No, but like, because you factored it out, it's like ax bxc wasn't u, it was e to the minus I alpha u.
Yeah.
So then when you factor it out,
it's just that.
I'm not following. Like why?
I mean, this is a tensor, yeah? I mean, this is why I wrote this down, so that I can see it, right? Because really, I'm just
Oh, okay. Now I get it. Yeah. Okay. Yeah. Okay. Now I do. Yeah.
Yeah, I had to think about it too, because they don't explain that in Nielsen Twine at all. At all. They draw this, but they don't explain it. They just boom. But yeah.
Okay. I felt like for some reason it went to both, but no, it only goes to one of them. Okay.
So I think that's amazing. Really impressive piece of work. And extremely important, yeah, because now we're going to get everything down to controlled U's, and we know that from controlled U's it's simply single qubit operations and C naughts. Okay. Later we will show that single qubits, unitary qubits, can be approximated with just Hadamard and T-gates. And so then we only need to do Hadamard, T-gates, and CMOS. Right, maybe I should have a sip of water. I think I'll deserve that. Now, what I want to show first is that if we have controls on more than one bit controlling this, and this may be on more than one, could be on more than one operation. In fact, it doesn't matter. You can still decompose it using Toffoli. So let's do that first. I'll leave that circuit out there because it's just so beautiful. So if we have control, on more qubits, like in Toffoli. So remember the Toffoli, we only flip this last bit if both of these first two qubits are set. Okay, so that was the Toffoli gate. So maybe we have 3 control bits, and U acts on these. So this would mean that U is acting on these 2 qubits and is controlled by these 3. Okay, so this would be, for example, I use a 2-qubit unitary operator. And here is control. So we want to see, well, what we can do in these cases. So this would be a tricky case. So let's just simplify it down to let's say we have, like a Toffoli, in the Toffoli case, this situation. What I want to convince you is that this is the same as the following circuit, where I introduce a third one here, a Toffoli here, control U there, and probably another Toffoli here, I guess. Okay, so I think that should work. So let's just put some letters in here so we see what we're talking about. So this is C1, control 2, T is coming in here. What this will do is nothing here, and here it will take, it will go to U to the C1, C2, T. Okay, so it will apply the U if both of these are set. Okay, so you're thinking this is a 0 or 1. Okay, there's a 0, 1. If one of them is 0, then this is 0, and nothing happens. If they're both 1, then this is 1, and you apply the U. Okay, so here it's got C1 coming out the other end again, C2. Here I'm going to put in a 0. This will only get flipped if both of these are 1, but then it gets flipped back again here, so at the end it still comes out as 0. And now this is going to be flipped to 1 if and only if this Toffoli has both 1s. And now it's a 1, it applies the U. So in exactly the same way, this is going to go only applied if both the C1 and the C2 are set. Okay, so this is actually equal. These two circuits are equal. So what we're proving here is that if U is controlled by multiple qubits, then you can actually do it just with Toffoli's and a single control U. Now we've already dealt with a single control U. That can be done with, as we just saw, C0s and single qubit operations. In exercise 4.4, you'll prove the same thing for Toffoli. So just to convince you that this kind of idea goes further. I don't know how you'd actually write down that complete proof, but anyway. Let's just do 4 gates. So let's suppose our U was controlled by 3. How would this then be implemented? So it might make a nice exam question to how many Toffoli gates do you need? How many control bits for that matter? 4 or 5 apparently. So apparently we need now 5, and then finding the U at the bottom. And now we've got to put in the Toffoli gates in the right order. So this is 1, 2 down to here. This then must be this one down to here, and that kind of makes sense. And then back the other way. Okay, so this then gets set if and only if the 3 are all set, right? Let's just check that. If both of these aren't set, then this won't get into a 1. This won't get set, so this one won't. If they're both set, then this is set, and then if this is set as well, then this one gets set and the U gets things. So this is the C1, C2, C3 here. So here you get C1, C2, C3, 3 control bits, and here you get the U to the C1, C2, C3, T. And likewise here. And these kind of dummy qubits get returned to their original state. So you just put zeros in here and they come out 0. So nothing happens here. Now, yeah, I'm not quite sure about the 2 qubit things. I have to look into that. I can't remember offhand what happens. How you break that down. Of course, we'll do that later. That's what we're going to do now, of course. Yes. So now we're going to prove. So what's the plan now? And now things really do get difficult. So now we're going to prove that an arbitrary unitary operator can be broken down into discomposed down into 2-level unitary operations. Yes, and now after that we will prove that the 2-level ones are equivalent to Toffoli's and controlled U's, which we've already dealt with. Okay. So rewinding back, what we need to deal with now is arbitrary unitary operators. And I'm looking at the time and I'm wondering whether I can fit in this one-page proof within half an hour, and I'm doubting myself. So I might have to finish this proof off next time. And that's good, because when I was going through this before the class, I realized that there's a slight thing missing, which of course, doing what every other teacher does, leave that as an exercise, when you suddenly realize there's a gap in the proof. And the reason there's a gap in the proof is because I couldn't find a proof of this, so I had to come up with my own one. In Nielsen Schwann, they just do the example R is 3, but it's not very illuminating and it's a little bit messy. And here I just tried to do the whole thing. So this is from page 100. You can have a look at yourself on page 199. And what we want to show is the following theorem, which they only prove for D is 3. So a unitary matrix what I know for us, our space is a Hilbert space, and this has got dimension d to the 2 to the n, but believe me, it's just easier if we just stick to this is just a normal complex space, any complex space. Can be written, I mean, later, of course, we will substitute in 2 to the n, can be written as product of d at most, well, in fact, d choose to 2-level unitary. So here's my proof. I have half an hour, maybe possible. Okay. So I claim that it suffices to prove the following. Okay, so we will prove kind of. There exists UD, U2, such that so I claim that there will be unitary, we will prove this, that we can find U2 up to UD such that this, which are unitary matrices that when we multiply by this is U, we end up with 1, 0, 0, 0 here, and then just a D minus 1 by times D minus 1 matrix here. And then I claim that this is enough because then we can just do the same with this matrix and decompose it more. This implies that there is this Uj such that. So this will be D plus D minus 1 plus D minus 2 plus D minus 3. And I don't have to tell you that D choose 2, choose 2 minus 1, down to UD, down to U1 is equal to the identity matrix. Okay, so I then apply that iterative. So applying this iteratively implies that there is uj. So we go all the way down to the identity, which now just means that u1 is. Oh, so I should have said unitary two-level unitary. That u1 is now u2. So it's in fact one less. I believe. Okay, so all I'm going to do now is prove this. Are you happy with that? Adrian, you convinced that if I can prove that, then this is... Yeah, okay, so this is just what I have to prove. Well, not bad. We're almost 200 pages through the book. It's only 600 pages, so we're a third of the way. We're going to get there. Now, yeah. So I'm going to define matrices. Let V1 be U. Vj. Yeah, so Vj is going to be the matrix. Well, writing over the I've unfortunately got three subscript things, so I'm going to put the j up there. Okay, so this is going to be Vj in general. From there, I can define Uj. So if this is Vj, Uj comes from the last one. So it has this very nice form. Okay, so it has 5 terms. Uj is, and it's based on Vj minus 1. Okay, so let me just copy this up because it'll be quicker. And this is complex conjugation to start. Okay. Oh, maybe I should put a j minus 1 in. Maybe I can just do the bar. That'll be easier. I've got room for my j minus 1. Okay, so this is going to be my uj, which you can verify is a two-level unitary operator. So it only affects the 1 and the j coordinates. The rest of it is just the identity. Okay, so you just basically got identity here, and this is another way. It's really nice to have the bracket notation, and then you've got your 4, essentially your 2 by 2 matrix there. Okay, so this is going to be a uj, and it's based on Vj, and it shouldn't be all starred, right? There's otherwise it's not unitary. Not really unitary. Okay, these one there. Right. So now so I have Vj minus 1. That gives me uj, and then Vj is uj vj minus 1, right? So let's see, what's v2? So v1 is u2, so it's, yeah, so this means that v2 is u2 times u1, and u2 is almost like u1, except you've done some funny operation between the first and the second in the top left-hand corner.
Where do you get the orthonormal basis in the V, or we're going to get to that after?
What's that?
Where the V's and the orthonormal basis, like where do you get those from, or we're going to do that now?
Orthonormal basis.
Like the ILs and the ones and the.
Yeah, that's just this is just the canonical basis.
Oh, so like any of it will do, or just.
Yeah, any one will do.
Okay. And then the V coefficients, we have to find those, or we also have them?
The V coefficient.
We haven't defined them yet, right?
Yeah, I think essentially we have, because we define V1 as U, right? And now that gives you U2 in terms of U1, in fact.
Oh, okay.
Yeah.
Okay, and then okay.
Because it's
Yeah, okay. I didn't catch that. It was J minus 1, so you had those. Okay, great. Thank you.
All right, so we just got to get down to this, which we're almost going to do, but I know at the end I forgot to. There was one little thing that I forgot to do, but I think essentially this works. I mean, so otherwise I wouldn't be stick up on the board for you. So by induction, what we'll try and prove. So by induction on J, we want to show that basically the first column has quite a lot of zeros in it. So V, and unfortunately I use K, which is probably a really bad letter to use, at least for me. Up to J. Okay. Would kind of like make more sense if the J was the K and then the K was the J, then it would be like kind of the index. But anyway, so this Vj in the first column has something here, and then zeros, and then something down here, and then a little bit of matrix. Okay, so this is going from 2 up until J. Okay, so we just want to prove that this, defining things like this, you get zeros here, and that's not going to be too hard to show. So for J is 1, it's true. It's trivially true. Because for J is 1, we're not claiming anything. Okay? So J is 2, there's a 0 suddenly appears in V2. But we will prove that as part of the induction step. So all we have to do is calculate Vj. Because we have Uj and Vj minus 1, and we just got to calculate it. So the idea being that really, this is only going to be 5 terms. Okay, so we do this term. What do we get left in this sum when we have this term? Okay, so we get the 1 with the I, so the I must go to 1. Okay, so we get the sum over L of V11 J minus 1 conjugated times V1L, and then this is a 1 L. Okay, so all I've done here is I've multiplied this term by this sum. And if you use the fact that these are it's an orthonormal basis, so it must just set I to 1. And I've got to do the rest with another 4 terms, and then that's it. Then you'll see that these are 0. Okay, so let's just do that. So plus so this one now is going to get this J. This is going to be set to J. So sum over L Vj1 J minus 1 bar Vjl J minus 1. This is J minus 1 here. They're all J minus 1. And then you get a Jl plus third term here. And now again, it's going to be this Vj1 J minus 1. And to get that, you need the 1 there. So you need V1L J minus 1 and then 1L. That's 3 terms. The 4th term, is that real minus? Yeah. Minus sum over L. So this is J, so it's going to be a J here. So we've got the V11 J minus 1. And then this is going to have to be a J to survive. So that's a VJL J minus 1 JL. And finally, the final term, well, here you get again the sum over I, yeah, so and I changed the letter, but in essence, it's the same thing, right? So, I want to change the letter because I think I changed the letter because I realised at this point I have the sum over I here and the sum over I here, and of course they're different I's. So I changed that mentally. I changed that L. That out I to an N, and then the L's get hit with the I's here and change that to an L. Okay, so that's right. So that's the final term coming from this matrix multiplication here. And that's it. So now what we need to check is that indeed we have these zeros in the first column. So the VK1J should be 0. So where is VK1? So we're looking for the coefficient, so VK1J is coefficient of J1. Where do you see J1 there? Well, you don't see any here. And you don't see any here either, unless K is equal to J. So it's clearly 0 unless K is equal to J, because there's simply there's no smaller ones. You don't have 1 or J in this, can't be a 1. So you don't get the term here. So it must be from these first 4 terms, and then these first four terms either have a 1 or a J at the beginning. Oh, sorry, so there's K1. So it's not as good as 0 for K is 2 to J minus 1, since they're just not there, right? They're not here because I can't get a 1 in the second term here. This L doesn't go equal to 1. And they're not here either because in the first term, these are either 1s or J's. So this K must be up to J. So now we just have to check for for J1, and J1 is, what's J1? It should cancel, so it would be the one thing here minus the one term here, which I may have dropped some conjugate somewhere. Let me just check that. Help! Here I only have the conjugates with the ones. Yeah, there's something wrong somewhere. I think this conjugate is not here because the conjugate here is with the one. So the conjugate here should be over here, and this one is not conjugated. Okay, because it's coming from this one. So somewhere I went a little bit wrong when I did that multiplication. B. Either that or I wrote it up wrong. B1J conjugate. So I don't know how I managed to do them in the wrong order. I mean, I've got the J here, so this must be from this term, right? And this must be from this term. So I don't know. I don't quite know how I managed to mess up the order there. But now you see that the J1 here is coming from here. This is VJ1, J minus 1, VJ1, J minus 1, minus the same thing here. Oh, should have been V11. It says here it should come from the third and fourth terms. So I've done something wrong. Okay, I think the problem is that I copy things down wrong. So this should have been 1L, VJ1, VJL, VJ1 bar, B1L, which comes from that. Then this should be VJL, VJ1, and then V1L, that's correct. And then here, without the bar, no bar here, and then this is from that term, V11, VJL. So now when I look at the JL, I have to take L equals 1, and I get VJ1, V11 here, and here I get V11, VJ1 here, with L equals to 1. Okay, and all of them with their J minus 1s up the top. Okay, so this is coming from the third and the fourth term is the only way to get J1. I think I made a mistake when I just applied the UJ. I somehow got my terms mixed at some point. But I think I'll leave that up there and you can check that that is correct. Now, the bit that I didn't do was the scaling. Now, I want to show you that U is basically almost unitary, because here, what can I rub off? Let's get rid of this bit here. So this U here, what am I doing for time? So this U here, basically, this is all trivial on these non-2 bits, and here you see you have a U is a 1, 1. The JJ term is minus that thing, and then you get a B and a B bar. Okay, so U bar is A bar minus A bar, B bar, B. So U bar is AA bar plus B this way. Oh, I forgot to, I just conjugate and then transpose, of course. B bar, AB minus oh, sorry. This is this was A bar here. Yeah, A bar here. So this is no longer A. Okay, so this is AA bar plus BB bar. A bar B minus A bar B is 0. AB bar minus AB bar is 0. And here we have A bar plus B bar. Okay, so up to a scalar factor here, this U is unitary. We've proved this is 0 up to here. So the final bit of the stage will be, you have to scale the U so that it is unitary, which I forgot to do, and prove at the end, when you get to VD, so we have VD is zeros all the way down to the end. Okay, you need to prove that this first thing is 1, then since all of these U's you scale them so they're unitary, when you substitute in here, this VD is unitary. So you end up with this VD is unitary. So if you have along here some numbers, then when you do VD, is equal to 1, and that implies that the other V's, these all V's along here are all 0. So which implies that. Okay, and that's what we wanted to prove. So we already agreed that if I could prove that we got it down to this with the production of with the product of 2-level unitaries, then iteratively we can go on and prove it all the way down. So the gaps in the proof here are proving that we scale it, the U's, so that this is 1. Well, that's just dividing by some determinant each time. And that when we do that, we end up with a 1 here. If not, we cannot use this argument that these are all 0 at the top. Okay, so that remains to be done. But yeah, I thought I'd give it a go, and it's also a nice example of the Dirac notation again coming to your help. You can really multiply really horrible matrices together just using this notation, which I think is, yeah. So, well, it was a brave attempt. I think we'll put that down in the book of brave attempts, and we will now use that. So conclusion today, we proved control U can be implemented with single qubit operators and the C dot. Arbitrary unitary transformation can be decomposed into two-level unitary operations. What's left to show? We need to show that a two-level unitary operation can actually be implemented with Toffoli and controlled U, and a unitary on just one qubit. Okay. Once we've done that, I think we're pretty much just found then to proving that we can implement a single qubit operator and together with the C naught, that will do it. Okay, so yeah, it's fun. I mean, the exercises are more practical. So I've talked a lot about the theory. So we will start them next week, because on Tuesday first we still have to do the exercises from quantum mechanics. So do email me over the weekend if there's any problems, and then we will go through them on Tuesday, and next Thursday we will continue with quantum computation. Okay, and thank you, Adrian, for having at least somebody to look at. And I'll see you on Tuesday.
I have a question.
Yes.
Why, when we go through this matrix iteratively, why we end up with D choose 2 matrices? I don't see that D choose 2.
Well, because we're summing. So the first time we get out with D, and then we got down to a D minus 1 by D minus 1 here. Okay, so then we have to add on D minus 1, and then next time it's going to be D minus 2, and down to the end. So it's the sum of J, and J is 1 to D, which is D choose 2.
Okay, yeah. Yeah, true. Yeah. Thanks.
Okay, so try and stop this.
No, it's D minus 1. Like you never have D, right?
Oh, sorry.
D minus 1.
Yeah, start with D minus 1.
Yeah.
Sorry,
Like that.
You got me worried now? Yeah, that's right. Yeah. Okay, let's see if I can stop this.